So in this pencast, I would like to talk about energy balances, and I'd like to start with a general approach, and then we can always dive into the more specific scenarios. So I'd like to think of it as a balance between, on one hand, I just need a little bit of color here. Sorry. On one hand, the cause, and then the effect over here. And let's start the equation by the equation sign here. And over here we can think of different causes. So the effect, let's start with the effect. That's a change per time unit in internal energy of the system, kinetic energy, and potential energy. That's kind of the energy forms that we could think of might change. And the reason they change, the cause, if you like, is that we supply or take out heat. Another reason could be that we do some work to the system, or the system does work to its surroundings. Yet another reason could be that there's a flow in and out of the system. So that flow brings energy to the system, because the constituents of flow contain internal energy. And finally, we could think of if there's a chemical reaction taking place inside the reactor, that can change the energy of the system as well. And I would like to take a look at each of these contributions here. Let's start with the heat here. So maybe we supply heat, from an electric heater. I'll just call it a heat supply. Or maybe there's just a heat exchange between the reactor and the surroundings. And we know that can happen by means of conduction, heat conduction, or convection, or even radiation. If we look at the work contribution here, that could be like an agitator that rotates in the liquid in the reactor, and that actually means that it supplies energy to the system. It's not really a considerable amount, unless the fluid is very viscous. Then it might be something worth taking account of. Also, volume work. If our liquid expands, maybe because it's heated, then that does work to its surroundings. But again, it's not really an important contribution. Then there's the flow term here. Well, that I said before, that if matter flows into the system, well, that internal energy of that matter flows with it into the system. Also, if there's a phase change going on in the system, that changes the internal energy of the system as well. And the flow has some speed, so it brings about a change in kinetic energy to the system. And if the flow is directed into the reactor at some height, some level above the reactor, then it actually drops in the gravitational potential, and that means it brings about energy in the form of potential energy as well. And finally, the reaction term here, well, that's basically chemical bonds that are broken and created, and that means that, well, that can generate heat or absorb heat as well. So typically, we would disregard some of these terms because they're not really important. I'll just change the color here. Kinetic energy contribution is typically small, so is the potential energy contribution. It's typically small compared to the internal energy of the flow. So we typically disregard those contributions. And in fact, the kinetic energy and the potential energy of the system itself won't change much compared to the internal energy. So we will allow ourselves to disregard those terms. Also, in many cases, we can actually disregard this term here because it's negligible compared to the heat that we might supply or the heat that is exchanged with the surroundings and the reaction energy and the internal energy of the flow. So that certainly simplifies our equation quite a bit. So here I've written the simplified version of the heat balance. And as always, we like to think of scenarios in which either of these terms vanish and become zero. So let's start with the first, the heat term here. Well, if we have what we call an adiabatic process, that means it's a process where heat is not exchanged with the surroundings. Well, obviously, this term then is zero. If we have a closed system, well, that means nothing enters or leaves the reactor. Well, then this term here is zero. And if we have a non-reactive system, obviously no reaction takes place and there is no heat of reaction. And finally, if we have a steady state system, then no changes will occur in the system, and that means this differential term over here will become zero, and our differential equation becomes an algebraic equation. So that's the general heat equation, and or the general energy balance, sorry. And we will do some specific examples using this heat energy balance in the next podcasts.